In May of 2021, a Cornell University research team published something that sounds, at first, like it belongs in science fiction rather than a peer-reviewed astronomy journal. Voyager 1, the most distant human-made object in existence, was picking up a signal. Not from Earth, not a command being sent out, a signal arriving from interstellar space. Itself, faint, steady, and completely unlike anything scientists had detected before. Before going any further, it's worth being direct about what this isn't, because the word signal carries a lot of baggage, especially when it gets attached to a spacecraft that's been drifting through the dark for nearly half a century. This isn't a message. It isn't artificial, and nobody studying it believes it comes from anything resembling intelligence, deliberate transmission, or communication of any kind. What NASA confirmed is something quieter and, in its own way, just as remarkable. For the first time in human history, an instrument built by our own species is continuously listening to the actual texture of the space between the stars, and it has been quietly humming back a signal ever since, one that nobody specifically designed it to catch in the first place. To understand why that matters, you need to go back to what Voyager 1 actually is and where it's been. Launched in September of 1977, Voyager 1 took a faster, more direct trajectory than its twin, Voyager 2, flying past Jupiter and Saturn before angling sharply upward, out of the plane the planets orbit in, aimed toward the edge of everything the sun's influence can reach. In August of 2012, it crossed the heliopause, the boundary where the sun's outward-blowing bubble of charged particles finally gives way to true interstellar space, becoming the first human-made object to leave the solar system entirely. That crossing wasn't even a clean story to tell at the time. The instrument best suited to directly confirm the transition, Voyager 1's plasma spectrometer, had stopped working back in 1980, more than 3 decades before the spacecraft ever reached the boundary. Without that instrument, NASA's own scientists spent 13 months arguing over the indirect evidence, a sudden drop in solar particles here, a jump in high-energy cosmic rays there, before finally feeling confident enough to announce that Voyager 1, scenario where one had genuinely left the solar system. With the primary plasma instrument dead, researchers had to get creative about how to measure anything at all about the environment Voyager 1 was now traveling through. That's where a different piece of hardware, one nobody had originally designed with this exact use in mind, ended up carrying the entire story. Voyager 1 carries an instrument called the plasma wave subsystem, built around 2 long antennas, extending outward from the spacecraft like thin metal whiskers. Its original job was to detect radio and plasma wave emissions in the environment around Jupiter, Saturn, and the other giant planets it flew past decades ago. It was never specifically built to eavesdrop on the near-total emptiness of true interstellar space. But plasma, whether it's swirling around Saturn's rings or drifting quietly between stars light years apart, behaves according to the same basic physics, and that same instrument turned out to be exactly the right tool for a job nobody had originally planned for it. Here's the physics in plain terms, because it's the key to the entire discovery. Interstellar space isn't a true, perfect vacuum. It's filled with an extremely thin, mostly invisible soup of ionized gas, plasma, made of free electrons and charged atomic particles drifting at incredibly low densities, often just a fraction of a single particle in every cubic centimeter of space, a density so low that a cubic meter of ordinary Earth air, by comparison, contains more molecules than exist across an entire acre of that interstellar plasma. When something disturbs that plasma, a shock wave from a distant stellar event, or a burst of material thrown outward by our own sun, the electrons inside it start to oscillate, vibrating back and forth at a specific natural frequency that depends directly on how densely packed those electrons are, the same basic principle that determines the pitch of a plucked string based on its tension and length. Voyager's antennas can pick up that oscillation as a radio frequency signal, and once scientists convert it into a range, human ears can process, slowing and shifting the frequency the way you might slow down a bat's ultrasonic call until it becomes audible. It comes through as a distinct tone, sometimes described as a whistle, rising and falling depending on exactly how thick or thin the surrounding plasma happens to be at that moment. For years after the 2012 crossing, that's the only way scientists could measure anything at all about the plasma surrounding Voyager 1, waiting for something dramatic enough to rattle it into making noise. The first of those events came in November of 2012, just 3 months after the spacecraft had crossed the heliopause, when Voyager's instruments picked up a burst of oscillation triggered by a shock wave rippling outward from an earlier solar eruption, a disturbance that had left the sun months earlier and traveled billions of miles before finally catching up to where the spacecraft happened to be. Researchers described it as hearing interstellar sounds for the first time, a brief, unmistakable whistle, rising out of what should have been silence. And picture the strangeness of that moment for the scientists on the receiving end. After decades of assuming true interstellar space would register as pure, featureless quiet, the very first thing that region of space actually did, once someone was finally listening, was sing. 6 months later, in April and May of 2013, a second, louder, higher-pitched whistle arrived. This one suggesting the surrounding plasma had grown noticeably thicker in just those few months of travel. James Cordes, a Cornell astronomy professor who worked on the mission's data, offered a simple way to picture what these events actually represented: the interstellar medium. Itself behaves like a quiet, gentle rain, and catching one of these solar-triggered bursts was like detecting a single, sudden lightning strike inside that rain, a brief flash of noise before the quiet returned. That analogy captures exactly why researchers were stuck for years afterward. Lightning strikes are dramatic, but you can't build a continuous weather map out of occasional lightning alone. Between those solar-triggered bursts, Voyager's instruments appeared to fall silent, and scientists had no reliable way to measure the density of the surrounding interstellar plasma, except by waiting for the sun to cooperate, sending out an outburst strong enough and aimed precisely enough to eventually slam into the region of space Voyager happened to be passing through. That's an enormously inefficient way to build a scientific data set, entirely dependent on the unpredictable timing of solar activity happening to line up with wherever a single spacecraft happens to be drifting, light years from any backup instrument that could double-check the reading. Then, in 2017, a Cornell doctoral candidate named Stella Koch-Ocker was combing through Voyager's data when she noticed something odd sitting quietly underneath everything else. Not a dramatic spike, not a whistle triggered by any known solar event, just a faint, narrow, oddly consistent signal that didn't seem to be going away. Ocker has described her own reaction to the moment plainly. Staring at the plot, she wondered if she was starting to see things that weren't really there. She wasn't. What she'd found was a persistent, low-level hum, distinct from every previous shock-triggered whistle in the data, sitting in a narrow frequency band and remaining detectable. Continuously, not for hours or days after a single triggering event, but for months and eventually years, without ever fully fading away. Unlike the loud, sudden lightning strike whistles that had come before it, this new signal behaved like the gentle background rain Cordes had described, except now, for the first time, that rain itself had become directly audible without needing a lightning strike to reveal it. That distinction matters enormously for what it lets scientists actually do with the data. Shami Chatterjee, another Cornell researcher on the team, summarized the shift plainly. For the entire history of studying interstellar plasma density up to that point, researchers had no reliable way to measure it except by waiting for a fortuitous solar event to happen to trigger a detectable whistle. Now, with a continuous, always present hum instead of an occasional unpredictable spike, that dependency disappeared entirely. Voyager didn't need the sun's cooperation anymore to report back on its surroundings. It could simply keep reporting continuously on its own, the way Chatterjee put it. The spacecraft was effectively saying, here's the density I'm swimming through right now, and here it is now, and here it is now, over and over, without pause, for as long as the instrument kept functioning and kept traveling through new territory. The research team's formal analysis, published in Nature Astronomy under the title Persistent Plasma Waves in Interstellar Space Detected by Voyager 1, confirmed the signal had already lasted nearly 3 years by the time of publication, a duration corresponding to roughly 10 astronomical units of the spacecraft's own travel through space, something on the order of 930 million miles. That's not a brief flicker. That's a signal steady enough and long-lasting enough to describe an entire stretch of the interstellar medium as Voyager physically passed through it. Plasma density readings arriving continuously across a swath of space nearly 10 times the distance between the Earth and the Sun. Ocker described the character of the signal itself in a way that captures how genuinely strange and delicate it is. Very faint and monotone, confined to an extremely narrow slice of frequency. Nothing like the dramatic, punctuated whistles that had defined every previous measurement. It's worth being honest about what all of this actually reveals scientifically, because the discovery's real value isn't mystery for its own sake. It's data. Before this persistent hum turned up, scientists studying the density of the very local interstellar medium, the small bubble of space in our own galactic neighborhood, had almost no direct, continuous measurements to work with, relying instead on scattered, indirect estimates and the occasional lucky solar-triggered event, the astronomical equivalent of trying to map an entire coastline using only the handful of moments when a storm happened to wash debris ashore. With Voyager's newly discovered hum providing a steady, ongoing readout instead, researchers gained something close to a live density map along the spacecraft's actual path, letting them track subtle variations in the interstellar medium as Voyager physically moved through different pockets of it, region by region, month by month, without needing to wait for the sun to cooperate first. That kind of data, feeds directly into broader models of how the sun's protective heliosphere interacts with the wider galaxy around it. Models that matter well beyond pure curiosity, since the heliosphere's shape and strength directly affect how much dangerous galactic cosmic radiation reaches the inner solar system, including Earth. There's a particular kind of poetry buried in the fact that this discovery came from an instrument nobody built for this exact purpose, riding on a spacecraft whose original 5-year mission ended decades before this data was even collected. Voyager 1 left Earth in 1977 carrying a golden phonograph record on its side, assembled by a committee chaired by the late Cornell astronomer Carl Sagan, engraved with sounds and images meant to represent human civilization to whatever or whoever might eventually encounter it drifting between the stars. Greetings recorded in dozens of languages, the sound of a mother's kiss, a baby's first cry, whale song, thunder, and pieces of music spanning cultures and centuries, all etched into a disk designed to survive, essentially unchanged for 1 billion years or more, far outlasting the spacecraft carrying it, quite possibly outlasting our own species. It's a strange, quiet symmetry that decades later, the very same spacecraft, still carrying that message outward toward whoever might eventually find it, ended up sending an entirely different kind of sound back the other direction. Not a message meant for anyone, just the raw, physical hum of the space. It happens to be passing through, arriving at Cornell as a signal instead of leaving as one, decoded not by an alien civilization discovering a golden disk, but by a graduate student staring at a plot of data one afternoon and refusing to dismiss what she was seeing as a glitch. The technical reality of how that signal even makes it back to Earth is its own quiet marvel, worth sitting with for a moment. Transmitting any data across more than 14 billion miles requires only about 22 watts of transmitter power from Voyager's side, roughly the output of a refrigerator light bulb, sent from a spacecraft carrying less computer memory than a single modern photograph, and originally designed to communicate at a data rate that today's home internet connections would consider unusably slow. Across that distance, the signal has degraded further still, down to roughly 160 bits per second, about half the speed of an early 1990s dial-up modem at its slowest setting. And yet, across all of that distance and all of that technological limitation, a signal precise enough to reveal the density structure of interstellar plasma still arrives, readable, usable, and scientifically rigorous enough to be published in one of the field's leading journals. Voyager 1 wasn't left to confirm all of this alone either. When its twin, Voyager 2, made its own separate crossing into interstellar space in November of 2018, 6 years later and at a completely different point along the heliosphere's surface, it carried something Voyager 1 no longer had, a fully functional plasma instrument, still operating after 4 decades in space. That gave researchers their first direct, on-the-spot plasma density reading, right at the moment of a heliopause crossing, rather than having to reconstruct it indirectly through wave oscillations the way they'd been forced to with Voyager 1. The two datasets lined up with each other well, enough to reinforce the broader picture emerging from both spacecraft. An interstellar boundary considerably more complex, porous, and structured than pre-Voyager models had ever predicted, with plasma densities and magnetic field strengths that needed real, on-site correction rather than theoretical guesswork. Having two independent spacecraft, crossing at different times and different locations, converge on a similar updated picture of the boundary, gave the whole body of research a level of confidence that a single data point never could have provided on its own. It's also worth being clear-eyed about how this discovery fits into everything else Voyager 1 has revealed since crossing into interstellar space, because it isn't an isolated curiosity. Once fully across the heliopause, researchers found the surrounding magnetic field measured 2 to 3 times stronger than pre-crossing models had predicted. Evidence the interstellar medium presses inward on the sun's own bubble with far more force than anyone had built into their simulations. The boundary itself turned out to be considerably more porous and irregular than the clean, simple edge older models assumed, with plasma bleeding across in both directions well before the spacecraft reached what was officially called the crossing point. The persistent plasma hum sits alongside those other findings as one more piece of evidence that the region where our solar system meets the rest of the galaxy is a far more active, structured, and dynamic place than scientists had assumed for most of the 20th century, back when the entire boundary was still purely theoretical, modeled on paper, rather than measured directly by anything humans had actually built and sent there. None of this means Voyager 1 has found anything artificial, intentional, or aimed at us. It's important to say that plainly because NASA confirmed spacecraft receiving signals from deep space is exactly the kind of sentence that tends to get stretched into something it isn't. What NASA and the Cornell team actually confirmed is narrower and in its own way more quietly impressive. A real, physical, continuously present hum generated by the ordinary behavior of electrons in an incredibly thin cloud of ionized gas, drifting between the stars long before humanity existed to measure it, now being picked up, translated, and studied by a piece of 1970s air hardware that was never specifically designed to hear it in the first place. All of this comes with a hard, ticking deadline that has nothing to do with the physics itself and everything to do with the hardware collecting it. Voyager 1 runs on a radioisotope thermoelectric generator, converting the steady decay of plutonium into electricity, and that power supply has been fading gradually and permanently every year since the spacecraft left Earth. Engineers have already had to power down instrument after instrument across both Voyager spacecraft simply to keep the remaining ones alive a little longer, and mission teams have said openly that within the next few years, the power will finally drop below what even one surviving instrument needs to keep functioning at all. That means the plasma wave subsystem, the same accidental instrument that stumbled into this entire discovery, is running on borrowed time. Every additional year of hum it manages to record and transmit back is added essentially on top of an already completed mission, a bonus dataset nobody planned for when Voyager 1 first launched, and one that will eventually, inevitably, go silent for good, long before humanity has any real prospect of sending a comparable instrument out to that same distance again. So here's where that leaves things, somewhere more than 15 billion miles. From Earth today, Voyager 1 is still moving outward, still carrying that golden record nobody has ever played, and its aging antennas are still, quietly, continuously, picking up the faint, monotone hum of the plasma it's currently passing through. Every few months, more of that signal arrives back on Earth, adding another stretch to the growing map of what the space between the stars actually sounds like, filled in not with silence, the way earlier generations of scientists assumed it would be, but with a low, steady drone that nobody on Earth had ever detected before 2017, and that nothing but this one aging, half-century-old spacecraft is currently in position to keep hearing. Think about what that actually asks of the people who built it back in the 1970s, working with slide rules and hand-soldered circuit boards. Decades before anyone had a name for the specific phenomenon, their instrument would eventually stumble into recording. They didn't design the plasma wave subsystem to listen for a continuous interstellar hum, because as far as anyone knew at the time, there was nothing continuous out there to listen for. They built the most capable, most general-purpose instrument the technology of their era allowed, pointed it outward, and trusted that whatever it eventually recorded, however far from home it traveled, would still have something worth saying decades later, long after everyone who built it had moved on to other projects, other careers, other lives. It isn't a message. It never was. But it's proof that even the emptiest seeming reaches of space aren't actually silent, and that somewhere out there, right now, an old machine built before most of the people watching this were even born is still faithfully reporting back exactly what that silence actually sounds like, one faint, monotone reading at a time, for as long as its failing power supply allows it to keep listening.